Welcome to our tutorial on TransformerDecoderLayer in PyTorch. Today, we're diving into one of the most important components of modern sequence-to-sequence models. We'll explore how the decoder differs from the encoder we studied previously, master its dual attention mechanism with both self-attention and cross-attention, and learn how memory from the encoder gets incorporated into the decoder. We'll also explore masking strategies specific to decoder architectures and build practical sequence-to-sequence models. This tutorial builds upon our previous work with TransformerEncoderLayer, where we learned how the encoder processes input sequences with self-attention. Now we'll see how the decoder adds cross-attention to incorporate information from the encoder's output, which we call memory. Let's start by understanding the key differences between TransformerDecoderLayer and TransformerEncoderLayer. The decoder has two attention mechanisms instead of just one. It uses both self-attention and cross-attention. It receives the encoder output as memory, which is a crucial input for the decoder. Often it uses causal masking to prevent looking at future tokens during generation. And it has three sublayers instead of two: self-attention, then cross-attention with memory, and finally the feed-forward network. The architecture comparison shows that while the encoder follows the pattern of input to self-attention to feed-forward network to output, the decoder has a more complex flow. It goes from target to self-attention to cross-attention with memory to feed-forward network, and finally to output. Let me set up our environment with all the necessary imports and configurations. We'll import PyTorch and its neural network modules, along with visualization libraries, to help us understand what's happening inside the decoder. Great, we're running PyTorch version 2.5.1. Our environment is all set up and ready to explore the decoder architecture. The fundamental difference between encoder and decoder is that the decoder takes two inputs. Let me show you the simplest example to illustrate this key concept. Here's our simplest TransformerDecoderLayer example. We create a decoder layer with a model dimension of 512 and 8 attention heads. Notice how we create two separate inputs. We have the target sequence, which is the decoder input with length 20, and the memory, which is the encoder output with length 10. Both have a batch size of 2. The key point here is the forward pass takes both target and memory as inputs. This is fundamentally different from the encoder, which only takes one input. Perfect. We can see that the target shape is 20 by 2 by 512, representing target length, batch size, and model dimension. The memory shape is 10 by 2 by 512, with a different sequence length but the same batch size and model dimension. The output shape matches the target shape exactly. The decoder successfully processes the target sequence using memory from the encoder. Let's look at the parameter documentation. Most parameters are identical to TransformerEncoderLayer, but there are some important decoder-specific notes. The D-model parameter must match the memory dimension. This is crucial. The N-head parameter is used for both self-attention and cross-attention. The dropout is applied after both attention mechanisms. When batch first is true, it affects both target and memory tensors. And when norm first is true for pre-layer normalization, it's applied to all three sublayers in the decoder. Now let's dive deeper into understanding the three attention mechanisms in the decoder. This is really the heart of what makes a decoder different and more powerful than an encoder. I'll demonstrate the three attention mechanisms in the decoder. We create a decoder with batch first set to true for clarity. We have a target sequence of 15 tokens and memory from the encoder containing 10 tokens. The decoder internally performs three operations. First, self-attention, where the target attends to itself, creating a 15 by 15 attention matrix. Second, cross-attention, where the target attends to memory, creating a 15 by 10 attention matrix. And third, the feed-forward network, which performs position-wise transformation. The information flows through these three stages. First, target self-attention learns relationships within the target sequence. Then cross-attention incorporates information from the encoder. Finally, the feed-forward network transforms the combined representation. Excellent, we can see the attention matrix dimensions clearly. Self-attention creates a 15 by 15 matrix where the target attends to itself. Cross-attention creates a 15 by 10 matrix where the target attends to memory. The information flows through learning relationships within target, then incorporating encoder information, and finally transforming the combined representation. The output shape is batch size 2, target length 15, and model dimension 256, exactly as expected. Masking in the decoder is more complex than in the encoder. The decoder supports 4 types of masks compared to just 2 in the encoder. We have target mask for self-attention, often a causal mask, memory mask for cross-attention, target key padding mask for handling variable length targets, and memory key padding mask for handling variable length memory sequences. Let me demonstrate all 4 masking types in action. We'll create a decoder and apply different masks to see their effects. First, we create a causal mask for autoregressive decoding, which prevents the model from looking ahead at future tokens. Then we create a target padding mask where the last 2 positions are padding. We also create a memory padding mask where the last position is padding. When we apply all these masks in the forward pass, they work together to control what the decoder can attend to. Perfect! Our mask configuration is working correctly. The causal mask prevents attending to future tokens, which is essential for autoregressive generation. The target padding mask ignores the last 2 target positions. The memory padding mask ignores the last memory position. We can see a mean absolute difference of about 0.137, confirming that the masks significantly change the output. All 4 mask types are working correctly. Let me visualize these attention patterns with different masks to help you understand how they affect the attention mechanism. Here we can see 3 different attention mask patterns. On the left, we have no mask, which allows full attention between all positions. In the middle, we see the causal mask used for autoregressive decoding, where each position can only attend to previous positions, creating this distinctive lower triangular pattern. On the right, we see cross-attention with padding, where certain memory positions are masked out to handle variable length sequences. With 3 sublayers in the decoder, using pre-layer normalization becomes even more important for training stability. Let's compare gradient flow in decoder versus encoder with different normalization strategies. I'm comparing gradient flow between post-layer normalization and pre-layer normalization for both encoder and decoder. We create both architectures with post-layer norm and pre-layer norm, then test how gradients flow through them. The gradient norm comparison shows dramatic differences. With post-layer normalization, we get very small gradient norms for both encoder and decoder. But with pre-layer normalization, we get much larger, more stable gradients. The encoder pre-layer norm shows a gradient ratio about 189 million times larger than post-layer norm. The decoder pre-layer norm shows an even more dramatic ratio of about 184 million times larger. This demonstrates that pre-layer normalization provides much more stable gradients, and this is especially important in the decoder with its additional complexity. Now let's build a complete sequence-to-sequence model using TransformerDecoderLayer. This will show you how encoders and decoders work together in a full translation or generation system. Here's our complete transformer sec-to-sec model. We start with embeddings for both source and target vocabularies, add positional encoding to give the model information about token positions. The encoder stack uses TransformerEncoderLayer with pre-layer normalization for stability. The decoder stack, which is the new part, uses TransformerDecoderLayer, also with pre-layer normalization. Finally, we have an output projection layer to map back to the target vocabulary. In the forward pass, we encode the source sequence to create memory, then decode with that memory from the encoder, using various masks as needed. The decoder output is then projected to vocabulary size for prediction. We also include a method to generate the square subsequent mask needed for causal, autoregressive decoding. Excellent! Our complete sec-to-sec model is working. We have a source vocabulary of 5,000 words and a target vocabulary of 5,000 words. The model dimension is 512 with 2 encoder layers and 2 decoder layers for this demonstration. The input shapes show source sequences of length 15 and target sequences of length 20, both with batch size 4. The output shape is batch size 4, target length 20, and vocabulary size 5,000, perfect for computing cross-entropy loss during training. The complete sec-to-sec model with TransformerDecoderLayer is working perfectly. Let me visualize how attention flows through the encoder-decoder architecture to help you understand the information flow. This visualization shows the 3 types of attention patterns in an encoder-decoder architecture. On the left, we see encoder self-attention, which is bidirectional, allowing each position to attend to all other positions. In the middle, we have decoder self-attention, which is causal or autoregressive, creating this distinctive triangular pattern where each position can only look backward. On the right, we see cross-attention, where the decoder attends to the encoder, allowing the decoder to incorporate information from the source sequence at each step of generation. Let's implement a practical example with a simple translation task. We'll create a toy task of reversing sequences to see the decoder in action. Here's our simple character level sequence reversal task. We create a vocabulary with special tokens for padding, start of sequence, and end of sequence, plus letters A through P. The task is to reverse sequences, so hello becomes ale, world becomes DL row, and so on. We create batches with source sequences and their reversed versions as targets, adding start and end tokens appropriately. The model uses our transformer sec-to-sec architecture with smaller dimensions suitable for this toy task. We prepare the data for teacher forcing, where we use the true target sequence shifted by 1 position during training. We can see our sequence reversal task clearly. Hello reverses to ale, world to DL row, decoder to redosed, and layer to rail. However, there's an error in the code with the mask generation that we need to fix. Despite this, the concept is clear. The decoder processes sequences with teacher forcing, using the true previous tokens to predict the next token during training. Now let's analyze the decoder components in detail to understand what makes it different from the encoder. I'm inspecting the decoder layer components compared to the encoder. Let's count the submodules and parameters in each. The component comparison reveals important differences. The decoder has 11 components, while the encoder has only 8. Both have self-attention with about 263,000 parameters. But the decoder has an additional multi-head attention component for cross-attention, also with 263,000 parameters. Both have similar feed-forward networks with linear 1 and linear 2 layers. The decoder has 3 layer normalization modules, norm 1, norm 2, and norm 3, while the encoder only has 2. The decoder also has an extra dropout layer. In total, the decoder has about 1 million parameters compared to the encoder's 790,000. That's a difference of 263,680 parameters, exactly the size of the extra cross-attention layer. The decoder-specific components are the multi-head attention for cross-attention, norm 3 for the third sublayer, and dropout 3. Let me visualize the parameter distribution in the decoder to show where all these parameters are being used. The parameter distribution shows that in the TransformerDecoderLayer, the feed-forward network takes up the largest portion of parameters, followed by self-attention and cross-attention, which are roughly equal. Layer normalization and dropout have minimal parameters. The bar chart comparison shows that the decoder has about 33% more total parameters than the encoder, with the difference coming entirely from the additional cross-attention mechanism. Let's review common pitfalls and solutions when working with TransformerDecoderLayer. First, forgetting the memory input. The decoder always needs memory, you can't just pass the target alone. Second, using incorrect mask dimensions. The decoder needs target length by target length for self-attention masks, not source length dimensions. Third, not using causal masks for autoregressive tasks. For generation tasks, you must always use a causal mask to prevent the model from cheating by looking at future tokens. Here's a summary of best practices for using TransformerDecoderLayer. For architecture, use pre-layer normalization for better gradient flow through the 3 sublayers. Ensure D model is consistent across encoder and decoder. Use causal masking for autoregressive generation tasks. Apply both target and memory padding masks for variable length sequences. The key differences from the encoder are that it always requires two inputs, target and memory. It has an additional cross-attention layer connecting to the encoder. It has about 33% more parameters due to cross-attention, and it supports 4 mask types, double the masking complexity of the encoder. Use the decoder for translation tasks, text generation with context, question answering, and any task requiring conditioning on encoder output. Finally, let me show you an optimized decoder configuration following all the best practices we've learned. We create a decoder with 512 model dimensions and 8 attention heads. We use a feed-forward dimension of 2048, which is 4 times the model dimension. We use GELU activation, which often performs better than RayLU. We set batch first to true following modern conventions. Most importantly, we use norm first equals true for pre-layer normalization to ensure stability with 3 sublayers. We test it with realistic inputs, including causal masks for autoregressive decoding and padding masks for variable length sequences. Perfect! Our optimized TransformerDecoderLayer configuration is working excellently. We've applied pre-layer norm architecture for stability, GELU activation for better performance, batch first format for modern conventions, the standard 4:1 feed-forward ratio, causal mask for autoregressive decoding, and padding masks for variable length sequences. The output statistics look healthy with a mean near 0, standard deviation around 1, and reasonable min and max values. All checks have passed, and this decoder is ready for sequence-to-sequence tasks. You now have a deep understanding of TransformerDecoderLayer and how to use it effectively in your projects.